So thank you for coming. Obviously, the Android talk is very interesting, and I have to say, if I wasn't standing up here, I'd probably go over there too. So, please ask questions anytime. Just raise your hand, and I'll get your question. If you want to wait to the end, that's fine too. So, I work as a security consultant, and this slide is just really in there because it needs to be in a slide presentation. So. I'm going to talk about the issue here at first, the attack, the cold boot attacks, in case you haven't heard about it or don't know that much about it, and we can talk about it, what it really is and isn't. And then I'm going to talk about a solution for it, FrozenCache. And I'll show you a demo, implement on Linux, and then we'll get to the questions that you want to save off to the end. So, cold boot attacks was a research that was done 2-3 years ago, and what they found is that, contrary to common belief, that when you take power away from a computer, then data in RAM will not immediately be erased, but rather it'll fade out over time. And a couple of seconds is common, but it can be extended up to minutes by cooling it. So the cold in cold boot attacks doesn't really apply to doing a cold reset on your computer, but rather to cooling the memory, the RAM chips. And they've achieved 10-minute periods where they still recovered significant portions of the memory. So when they found that, they combined that with the knowledge that when you have a full disk encryption or any sort of encryption software, that software needs to keep the encryption key in memory. So I thought, well, this is a security risk. Even if you have a locked up computer where you're using a full disk encryption and someone will not be able to get to it functionally in terms of logging in or anything, they can now use this attack, take out the memory, cool it, and put it in a different computer and run some program to extract whatever data is in the memory. And so Carsten told me just a couple of hours ago that this wasn't really that new of a research. He said that 10 years ago there was a paper or work done by IBM that had already found that memory doesn't immediately get erased. So what was new in this research was that it was being applied to software doing with encryption keys. So, and what's important to know is this applies to DRAM, which is RAM that has to be refreshed every so often to not lose its data. So, whereas some other memory types, they're static and they are not really that affected, but you don't use that type of memory as your memory. So, the solution to this attack scenario is, well, let's sacrifice some CPU cache which sits inside the chip and store the key there, and leave everything else out in memory. So when you try to apply the attack scenario there, you will not be able to get to the cryptographic key, because when you take out the memory, it's not in memory, and you can't really get to the key that's inside the cache because there's no external interface to read out the cache contents. And also when you reset the CPU, the cache gets erased upon CPU initialization. So really, to my knowledge, you have no way to get into that data that's in the CPU cache. So the concept really isn't mine. I was at the 25C3 CCC Congress, and Peter Stooge gave a talk about how Core Boot deals with certain issues. Core Boot is a Linux-based BIOS replacement. So at one point in his talk, he said, and we were having issues with memory controller initializations, because that all is low-level custom code that needs to be implemented for every motherboard and everything, every memory controller. And that's all really low-level custom assembly code that avoids using memory because the memory isn't there yet. So they were looking for a solution to sort of ease their way out of this complexity. And what they, I guess, discovered is that you can switch the cache into a certain mode, then you can use the cache as memory, and the cache accesses will not sort of push out into memory. So what they do is they activate this cache as RAM mode, and then just use standard C code to do whatever stuff they need to do to initialize the memory controller. Obviously, there's some low-level parts that need to be done there, but for the most part, it brought them simplicity, so they don't have to, deal with every sort of aspect of avoiding memory access. When trying to apply this to security in terms of trying to keep the key in cache only, it gets a little bit tricky. So there were some challenges that I was facing when looking at this. The first one is that x86 really has no cache management, so to say. When you, as a software, want to know about what's in the cache, what's the state of the cache, when has cache last been flushed, and all that, there's really not much there. So what you have to do now is find a way to make sure that what you put in the cache really will not automatically be pushed back into memory. And that's sort of what I get from the cache's RAM mode, is that it'll behave like that. But obviously dealing with the security scenario here, you want to be sure. So my first approach was to just refresh the moving of the data into the cache periodically. So just in case it does get pushed out, we'll move it back in and sort of play that game. And I thought, well, there ought to be a better way. And I came up with the idea of tricking the cache into holding data for a memory address that isn't there on the system. So if you have maybe 2 gigs of RAM, then you have the upper 2 gigs where if you had an address in cache that it tries to push out, then obviously the memory controller will tell it, no, I can't do that because I don't have that. And I really played around with that for a bit, and it didn't work out. I just could not get the cache to accept data for an address that wasn't existent. So if any of you, are like a low-level CPU assembly hacker that knows anything about this, any help is welcome. So the second challenge is, well, when you try to keep data in the cache, then obviously you're defeating the core purpose of the cache, which is to keep the most common data nearby the CPU so it's faster on access. And if you sort of say, okay, I want to keep just this data in there, then your computer gets slow. And I'll show you how slow it'll get. So one of the issues here is that because there really isn't any fine-grained control on x86 over the cache either. You cannot just say, okay, freeze the level 1 cache, but keep the level 2 cache going, because that's all on chip nowadays, and there just isn't any configuration options that the processors provide you with. What could be done is maybe activating a level 3 cache if the chipset brings it, provides it, but that's not anything that I have looked into just yet. So obviously with this scenario being so hindersome with performance, the question is, okay, how can we minimize the effect? Well, obviously the first part is activate the mode only when it really is useful. So if you're having a system that's running that isn't screen locked, there's no need to protect your key against cold boot attacks, right? So part one, only activated when it's really senseful. And for that, two things come into mind: when your screen is locked and when your computer goes into standby. I mean, standby, not suspend, where power is completely turned off. So, and another thing we can do is we can not only keep the encryption key in memory, in the cache, but also the most commonly used code, so that, you know, hopefully some parts of what your CPU is doing that's time critical is already there and you're not feeling the impact of that. But that all is really a lot of work in progress, so I'll get to that a little bit. And as a third challenge, there's an issue with the key itself. You think, okay, I have an encryption key, let's say it's 32 bytes. Okay, I just need to keep these 32 bytes in the cache. No, that's not the truth, because internally a lot of encryption algorithms will work where they expand on the cryptographic key that everybody sees and derive other keys from that that they then use for the encryption, decryption itself, and that's called the key schedule. So you now need to not only worry about the 32 bytes for the key, but also about all these derived keys, because if you have those, if you can extract those, they're just as good as the master key, so to say, because they're the ones that are being applied. And lastly, you have, during the computation, you have all these intermediary values that maybe you could exploit to do some cryptanalysis on the key, if you can obtain those values. So the solution for this is, okay, let's implement some hooks that whenever the software component that does all the disk encryption handles the cryptographic key, then we register that address for the key, and whenever I switch the mode on, then it'll just add this data into the RAM, into the cache. So that's fairly easy if you're worried about the key that that is sort of the encryption key. That is fairly easy for the key schedule, although that's a little bit more distributed. But that's really hard for any intermediary data, because you don't know where it is. It might be some variable that's put on the stack during the computation. It might be something that the implementation puts on the heap. So that really has to come down to a per implementation specific solution, whereas the other stuff can be sort of at the interface level, where you're saying, okay, this is my component for providing some sort of encryption. And I'm flying. I'm already at the demo. So what I'll show you is essentially how to activate it, how it can be integrated into the system, but it's not perfect yet. So it'll provide the protection that I'll talk about, but it's not, performance-wise, it's really awful. And in the description for this talk, I said that I'll release the source code. I'm not there yet, so I won't release it just yet. If you want to see it, we can go through it. If not, then, you know, just it'll be a little longer. So what I have here is a new entry in the proc file system, and if I write a 1 into it, it'll activate the mode, and if I write a 0 into it, it'll deactivate it. So, okay, that was quick. That's too quick. Let's see if it's enabled. No, it didn't enable it. Let's try again. Okay. As always, doesn't work. So what should have happened is that the activation kicked in, and when that happens, these lines right here, is that the enable caches RAM method is activated, and then all the keys that are relevant are then moved into the cache, and the cache then is frozen so that none of the data will get purged out of the cache. So I have no clue why it doesn't work, but I guess we'll just have to accept it. Performance-wise, you type in a letter, it'll take about a half a second for the letter to pop up. So that's sort of the level of performance we're talking here. So if you lock your screen and if you move your mouse for the password box to come up, it takes about 10 to 15 seconds. So obviously this isn't anything that you could make usable. That's the work that's left to do is the performance, adding the time critical stuff into the cache and all that. So what I have is for testing, I created some debus hooks that will activate FrozenCache mode when the screen locks. So that when the screen lock goes on, the script gets called, and it'll then just activate the mode. And obviously, when you unlock the screen, it should go back, but that wasn't just implemented just yet. So, are you interested in source code? Nodding. Okay. So, what I've done is there's the sort of the in it, the grunt that goes with writing a kernel module, and it'll initialize the subcomponents. So the init car is the cache's RAM part. Init encrypt will initialize the disk encryption module, and the reason that this is part of this module is that the hooks that are necessary to invoke the mode for the key registration, I really found no clean, no really good way to add that sort of dynamically, as in maybe rewriting a function pointer or something like that. That all didn't really look too good. So what I did is I copied the encrypt module, then included it as a part in this module, and in order to activate this module, I then blacklist the encrypt and list this module as a provider for the encrypt service. And of course, the init procfs provides the procfs entry where you can interact with it. So the encrypt module is really just plain. The only thing that's added to it really right now are calls to the function that registers the address of a key that needs to be protected when you activate the cache's RAM mode. And you can see it's inside a function. This function is static, so you can't get to it from the outside, from another module. So you could look up the address of it in the kernel and then jump to it if you just know the header format, and then try to maybe patch some jump instruction into it or anything like that. But that's just really a good practice. So adding these two lines will essentially tell the FrozenCache module about where keys are with respect to the master encryption key. Obviously, that doesn't include the derived keys or any intermediary data just yet. So cache's RAM mode is really a lot of work in process. It'll iterate over all the keys that I have, and the top instruction will flash out the cache, so everything in the cache is invalidated, so you have a really pristine cache that you can start with. And by switching on the non-interrupt mode, the CLI instruction, you can be assured that nothing else happens while you run through this. So by accessing the data, it'll automatically be added to the cache. And what I do is we take the key, load it into some registers, wipe out the memory, take the key, write it back into the cache, and then you essentially freeze it right there. So for copying the key into the cache, I use SSE registers because they're big. They provide up to 64 byte of storage capacity, so that you can copy 64 byte chunks of data into the cache, which is also usually the cache line size. So that works out real nice. And then you rewrite the cache so that it'll operate in the cache's RAM mode. And the SSE part is, like I said, it's just accessing the memory location for up to 64 byte, putting it in the SSE register, and then just dumping it where it belongs. So I'm sorry that it didn't work out. I'm sure if I reboot it, it'll work, but obviously not seen that behavior before. So, like I said, there's a dencrypt embedded in this module because there's no clean way to sort of dynamically add the hooks to it at runtime. And one thing I haven't touched is that there could be a race condition if you have multiple cores or processors, where while working on this, another entity, the kcrypt, the kernel task, which does the actual encryption and decryption of the stuff that needs to go to disk, if that accesses any of the data while it is being manipulated, moved into the cache, then obviously that's not good. So what needs to be done is the kcrypt daemon needs to be paused for the activation of the FrozenCache mode. So one thing that I would like to do for performance is, for multi-CPU systems, is to bind that kcrypt task to a given CPU, so that only this CPU needs to then be cache switched into the slow no-fail mode. Then maybe, I haven't tested it just yet, but maybe then you can still get real-life usable performance from the other CPU that you have where the cache would be activated. And that, of course, only works if you have an architecture where your CPUs don't share the cache. So hyper-threading won't work with that. But all the multi-core, well, most of the multi-core systems, they allow you to sort of do that and still get some performance. And the key schedule and the intermediary data is also not protected just yet. So that's all still outstanding. There's one issue that really is out there that I haven't tackled also, and that's cache associativity. Because cache is so small, like on my system it's 32 kilobyte, the level 1 cache, level 2 cache is a couple megabytes. You really have to figure out how to move data in there so that when you add another data item to the cache, it doesn't evict another data item that's already in there, because cache associativity only allows you to place certain memory addresses in certain address lines in the cache. So I'm thinking maybe of figuring out, okay, where would this address go into the cache? Is there already something I've assigned to it? If yes, am I over the limit for this cache specific? Maybe then I would implement something where that address is moved to another address, and the corresponding pointers that are used within the module would then be repointed to another address, so that then this new address could be moved into the cache. That's going to be a lot of work, so I'm through. Do you have any questions? then that's nothing holding us back from going to the party, right? All right, well, thank you.
Thank you very much.